Imagine a world powered by the smallest particles in the universe. These particles, invisible to the naked eye, hold the key to an almost limitless source of energy. Picture a future where our cities, homes, and industries are powered by this incredible force. Imagine harnessing the immense energy locked within atoms. Atoms, the building blocks of matter, contain a tremendous amount of energy within their nuclei. By unlocking this energy, we can tap into a power source that is both potent and efficient. This is the promise of nuclear power. Nuclear power plants are designed to harness this energy, providing a steady and reliable source of electricity. Unlike fossil fuels, nuclear power generates electricity without emitting greenhouse gases, making it a cleaner alternative. It's a source of clean, reliable energy that can power our cities and industries for generations to come. With the growing demand for energy, nuclear power offers a sustainable solution that can meet our needs without compromising the environment. Nuclear power plants, though complex, rely on a fundamental principle of physics: nuclear fission. In these plants, engineers and scientists work tirelessly to ensure the safe and efficient operation of reactors. The process of nuclear fission involves splitting the nucleus of an atom, releasing a significant amount of energy. This process, splitting atoms to release energy, is at the heart of every nuclear reactor. When the nucleus of an atom is split, it releases energy in the form of heat. This heat is then used to produce steam, which drives turbines to generate electricity. Understanding nuclear power begins with understanding this remarkable process. By studying nuclear fission, we can appreciate the science and technology that make nuclear power possible. It is a testament to human ingenuity and our quest for sustainable energy solutions. At the core of every nuclear power plant lies the reactor core. This heavily shielded structure houses the fuel that drives the entire plant. Within the core, uranium fuel rods are carefully arranged to initiate and control nuclear fission. These rods contain enriched uranium, the fuel that makes nuclear power possible. The reactor core is where the magic happens, where the immense energy of the atom is unleashed. Nuclear fission, simply put, is the splitting of an atom's nucleus. When a neutron strikes a uranium atom, it becomes unstable and splits into smaller atoms. This splitting releases a tremendous amount of energy in the form of heat and more neutrons. These newly released neutrons then go on to strike other uranium atoms, creating a chain reaction. This chain reaction is the fundamental process that allows us to harness nuclear energy. The chain reaction in a nuclear reactor is carefully controlled. Control rods, made of materials that absorb neutrons, are inserted into the reactor core. By adjusting the position of these rods, operators can regulate the rate of fission and the amount of heat produced. This precise control is crucial for safe and efficient operation. The chain reaction, while powerful, is kept in check, ensuring a steady and reliable energy output. Section 5. From heat to steam, the role of water in nuclear reactors. Water is an essential component in the operation of nuclear reactors, playing multiple critical roles that ensure the efficient and safe production of energy. The heat generated by nuclear fission is used to produce steam. When uranium atoms split, they release a tremendous amount of heat. This heat is harnessed to convert water into steam, which then drives the turbines to generate electricity. In most nuclear power plants, water acts as both a coolant and a moderator. As a coolant, it absorbs the heat produced during fission, preventing the reactor from overheating. As a moderator, it slows down the neutrons, making the fission process more efficient. It circulates through the reactor core, absorbing heat from the fuel rods. The fuel rods, which contain the nuclear fuel, get extremely hot during the fission process. The circulating water absorbs this heat, maintaining the reactor at a safe temperature. This heated water is then used to generate steam in a separate loop. In a closed-loop system, the water heated by the reactor core transfers its heat to a secondary loop, where it turns water into steam without mixing with it, ensuring safety and efficiency. There are two main types of reactors: pressurized water reactors, or PWRs, and boiling water reactors, or BWRs. Each type has its unique method of using water to produce steam. Both use water, but in slightly different ways, to achieve the same goal: steam production. In a PWR, water is kept under high pressure to prevent it from boiling, while in a BWR, water is allowed to boil directly in the reactor core. This difference in approach highlights the versatility of water in nuclear technology. Safety systems in nuclear reactors also rely heavily on water. Emergency cooling systems are designed to flood the reactor with water in case of an emergency, ensuring that the reactor remains cool and preventing any potential meltdown. The role of water in nuclear reactors extends beyond just the production of steam. It also plays a crucial part in minimizing the environmental impact of nuclear power. By efficiently managing heat and radiation, water helps in reducing the overall footprint of nuclear energy production. As we look to the future of nuclear energy, advanced reactor designs continue to innovate on the use of water. New technologies aim to make reactors even safer and more efficient, ensuring that water remains a vital component in the quest for sustainable energy. In conclusion, water is indispensable in the operation of nuclear reactors. From cooling and moderating to steam production and safety, its multifaceted role underscores its importance in the nuclear power industry. As technology advances, the role of water will continue to evolve, driving the future of clean energy. Section 6. Generating electricity, spinning turbines, powering the world. The steam produced in the reactor drives turbines, much like in conventional power plants. These turbines are connected to generators, which are responsible for producing electricity. As the steam expands and spins the turbine blades, the generator converts the mechanical energy into electrical energy. This electricity is then sent through transformers, increasing its voltage for efficient transmission over long distances. Section 7. Safety first, protecting people and the planet. Safety is paramount in nuclear power plants. Multiple layers of safety features are in place to prevent accidents and contain any potential releases of radiation. The reactor core is housed within a thick, steel-reinforced concrete containment structure. This structure is designed to withstand extreme events such as earthquakes and tornadoes. Additionally, emergency cooling systems are on standby to prevent meltdowns in case of a malfunction. Section 8. Nuclear power versus the alternatives, a comparative look. Compared to other energy sources, nuclear power offers several advantages. It's a highly reliable source of baseload power, meaning it can generate electricity consistently. Unlike fossil fuels, nuclear power doesn't produce greenhouse gases during operation, making it a carbon-free energy source. However, it also presents challenges, including the safe disposal of radioactive waste and the potential for accidents. Section 9. Challenges and concerns, addressing the issues. Nuclear power faces challenges that require careful consideration. The disposal of radioactive waste is a major concern. While the volume of waste is relatively small, it remains radioactive for thousands of years. Finding safe and secure storage solutions is crucial. Additionally, the cost of building new nuclear power plants is high, often requiring significant government subsidies. Section 10. The future of nuclear power, innovation and advancement. Researchers are exploring new reactor designs that are safer, more efficient, and produce less waste. Small modular reactors, or SMRs, offer a more flexible and scalable approach to nuclear power generation. Thorium reactors, utilizing a different fuel source, have the potential to address some of the limitations of traditional uranium-based reactors. Section 11. A sustainable energy future, the role of nuclear power. As we transition to a more sustainable energy future, nuclear power has a crucial role to play. In the face of climate change and the urgent need to reduce greenhouse gas emissions, nuclear energy stands out as a powerful ally. Unlike fossil fuels, nuclear power generates electricity without emitting carbon dioxide, making it an essential component in the fight against global warming. It provides a reliable, carbon-free source of electricity that can complement renewable energy sources like solar and wind. While solar and wind are intermittent and dependent on weather conditions, nuclear power offers a steady and continuous supply of energy. This reliability ensures that our energy grid remains stable and capable of meeting the demands of modern society. By investing in research and development, addressing safety concerns, and exploring new technologies, we can make nuclear power even safer and more efficient. Innovations such as small modular reactors and advanced nuclear fuels hold the promise of reducing waste and enhancing safety measures. These advancements can help mitigate the risks associated with nuclear energy and make it a more attractive option for countries around the world. We can harness the power of the atom to create a cleaner, brighter future for generations to come. Imagine a world where our children and grandchildren can enjoy clean air, pristine landscapes, and a stable climate. By embracing nuclear power as part of a diverse energy portfolio, we can move closer to this vision. Together with renewable sources, nuclear energy can pave the way for a sustainable and prosperous future, ensuring that we leave behind a planet that is healthy and vibrant for all.